So to do math in Roman numerals, addition more specifically, it's actually almost easier in Roman numerals than Arabic numerals or Arabic number symbols, which is what we use now, because it's simply combining all the numbers together and then breaking it down into its actual form. So to break a number down into its actual form, let's say we had like a number like this, where we had like 5x's, 2v's, and 5i's. That could be a number, but 5i's make a v, 2v's make an x, and 5x's make an l. So that's actually lxv, and not what I put down there. And this is much easier to read, because we can see 50 plus 10 plus 5, which is equal to 65. So then we can go and check that, because, you still make a couple of mistakes. But 65 near the top, lxv is 65, which is good to know. So that's basically how you read Roman numerals. And here are some questions I've done earlier. Here's a really simple one, 10 plus 10. X is 10, x is 10. Combine the two together to get 20. 15 is xv. 20 is xx. Combine them together, 3 x's, 1v. 35. 17 plus 29. 10, 5, 1, 1. 15, 17. 29, 2 x's, 20, 25, and then 29. And because it's addictive form, we're not going to write it like this. Because it's much easier, because then you have to, it gets very complicated very quickly, and it's much simpler to do addition in addictive form and multiplication. But that equals 46. When you combine them together, you get 4x's, 40, and 6, because two of the 5i's get combined. So we'll do one more, bit of a bigger number. Let's do 216 plus 162. Kind of random, but it works. So 200 is cc, plus, and 16 is xv for 15, and 1. 100, and then we can put an L here for the 50, and then 10. So this equals 60, and 2. Then we can combine them together. CCC, XX, V, I, and these two X's can be made into nothing. These three C's can't be made into anything. So this number reads 320, oh, that's bad. 328. And we can double check. 216 plus 162 equals 378. Didn't put the L in because I'm blind, but we can see that when we do actually put the number in correctly, that it reads 378. Take away the 5i's, get V, take away the 5 x's. How many x's are there? There's 5 x's, which means we can make them into an L. And 50 plus 50 is 100, so you can make it into a C. And this is now correct because it's 900, 500, 100, 100, 100, 100, and 5. And the answer is 905. So that's where it gets a bit complicated, is when you miss out the L. I miss out the L a lot. It's really annoying because they look like eyes. But what can you do? And that's basically it for how to add. It sort of just takes trial and error. It's almost easy. I find it easier once you get used to it than Arabic numerals, because you don't have to like do the one above there and then keep going down. But it gets a bit complicated, but a way to think of it is that it goes up in like powers of, like, not powers of 5, but it goes up in like multiples of 5. So we have 1, so we have 1, 5, 10, 50, 100, 500. So every time we get to like a 1 or a 5, 10 and 50, 100 and 500, and it keeps going on to 1000, which is m, that's when you make a new symbol. So you get up here, you can see 5 i's makes a v, 2 v's makes an x, and then back to 5 x's make an l, then 2 l's make a c, and then 5 c's make a d, and 2 d's make an m. And that's sort of how you add Roman numerals together and make them go up. And adding in subtractive form is a complete pain, and Romans didn't use subtractive forms when they used Roman numerals. It was only until the Middle Ages when everyone said, let's use this and stuff like this. And it makes no sense to me. The Romans only used it when they were short on space, but this was 4, and this was 9, and this was 400. And it makes everything much easier. Now multiplication is a bit more complicated and takes a bit more trial and error, but I'll try and explain it my best. So if we do a simple number, let's just do like a number we can easily do in our head, 8 times 4. Now there's a couple of ways to do it, but the way the Romans did it is they'd take 8, they'd take the two numbers, so they would take 8 and 4. Clearly I can't write 8, but now I can. And what we do is we create a table of halving these numbers. So we're going to half 8 into 4, half 4 into 2, and half 2 into 1. And then we do instead of halving this number, we double it. So we get 8, and then we get 16. Is that 12? No, that's 16. 15 plus 1, and 16 is 32. Relatively sure that's 32. 32. And then when all the numbers are even, we can just take this number here, will be the answer. Now if numbers are odd, let's do 7 times 4 as well, again. So let's half 7, and halving 7 is a bit weird in Roman, or Roman numerals, because you have to sort of ignore remainders. So to half 7, you get like 3.5, but you just write 3. And then to get 3, you just write 1. And doubling 4, pretty much the same thing. You get 4, 8, and then 16. Yeah, and then so 16 is not the answer. So we're going to add all of these numbers together. So we get x, v, v, I, I. And we'll start taking away these. 1, 2, 3, 4, 5. It's a v, 2 v's, make an x, and then we get 28. So that's the way to do it if you've got an odd number and an even number. So with even numbers, this is your answer. With an odd number and an even number, this is your answer. But if you have two odd numbers, let's keep it simple. 7 times 3, it's half 7. 7 doesn't really work, let's get 9. 9 is going to be 4, because it's supposed to be 4.5, but it's not. And then 2, then 1. If we double 3, I need to move all these down. So I can move these up. So we need to get 9. We need to get 3. We double 3 to get 6. We double 6 to get 12. That's 10 plus 2. We double 12 to get 24. And then what we do is we take all of the, if the numbers are even on this side, then we take them away from this side. So we're going to add all these together except where the corresponding right number does not work. So we can just cross them out. So these don't, so it's just these two which you're going to add together. So XX, I, and I, which equals a V. And then we have our answer, which is 27, which is correct because we can clearly see 9 times 3 is 27. So now let's do a bigger one, and this is where one tiny mistake ruins the whole thing, like normal math. Let's do 27 times 81. So let's write out 27 and write out 81. So L, X, 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 I. Now, it doesn't really matter which number you half. I think I'm probably going to half 81 because it's bigger, which means I don't have to go as high with 27. So now everything's sort of backwards, but that's fine. We can sort of move everything around to make it fit. So now let's half 81 to get, you know, a number. We'll get 40 because the 1 doesn't matter, so we can just put in 40. That's just mental math there. And half 40 is 20. Half 20 is 10. And then half of 10 is 5. Half of 5 is 2. And half of 2 is 1. So there's a lot of even number here, but it all makes sense after we double this. And it should give us the right answer, and I'm obviously going to double check. So once we start doubling bigger numbers, we get 4 x's, 2 v's, 4 i's, which can be read as, that is 40, and these 2 v's can be written as an x, which is 50. So we can write that as 54. Let's just check. Let's just double check that. Is 54. So now we have to double 54. Because we know it's 54, we can just do that in our head. That is 108. So we can do C, V, I for 108. 108, 216. Or you can go CC, VV, III, and then take away 2, 3, 4, 5 i's to get a V, and make these into an X. So now we have 210, 6, 15, 16. And then we have to do it again, 216. That is 432. And 400 is just going to be 4 C's. And 32. CCC, XXX. But let's see if that would work. So let's write it out in a sort of rubbish way. CC, CC, XX, VV, II. These two get made into an X. I'm pretty sure that's the number we had before. So we have 432. 432 is 800 and something. But if we write out 800, we have DCCC. And 32, we can write out XXX, XXX, II. 1, 2, 3, 4, 5 equals an L. And then we have 500, 600, 700, 800, 50, 64. So 864. And then finally we have DD, CCC, CCC, LL, XX, III, III, 5, V, just stay there, 2 L's, make a C, we have many C's, but that's fine, 1, 2, 3, 4, 5, D, 2 D's, make an M for 1000, and that should be our final number, 1,728. 1,000, I can't remember that number, I have to write it down. So that is 1,728. So 28 times 2 times 1, 2, 3, 4, 5, 6. So we're going to do 27 times 2, 6 times. 27 times 2, 2, 3, 4, 5, 6. So we can see that is correct. Now, that is not the answer to 81 times 27. So what we're going to do is all the even number ones. You can see this corresponds to 2, which is even, so we cross it out. 5 is not even, so we leave it. 10 is even, so we cross it out. 20 is even, so we cross it out. 40 is even, so we cross it out. But the important thing is, and what took me forever to figure out, is you actually need to keep the original number in order to get the correct answer. And even then, it's still very complicated. And I still get the wrong answer half the time. But I'm getting better at figuring out these big equations. So now we have M, D, C, C, 1, 2, 3, 4 more C's. There's no L's. So we're going to move on to X's. We'll start from the top. XX, XXX, XX, then V's, V, V, I's, 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 4, 5 is a V, 2 V's are an X, 2, 3, 4, 5, L, that's an L, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it's a D, 2 C's is an M, MM, CL, XXX, VII. So something, 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 7. Let's write that down as a number. 2,187, I believe. I'm just going to double check. So this is in the 2000s. So let's go into the 2000s. And obviously that doesn't exist. So something's obviously wrong here. 2,187. 2,187. Ah, and the reason it doesn't exist is because it's in the 2000s, not in the 1000s. And it is here. It's 2,187. So that is 2,187. But now is 81 times 27. 2,187. And it was right. So that proves after a week of doing it constantly, I can now do multiplication, and hopefully this has taught you how to do multiplication as well. Now the really important stuff is remember to keep this number, the original number, because this is 27. And you need to add that to all of them. So really it's just 27 plus 432. So it's sort of just basic addition. 27 plus 432 plus 1,728 equals 2,187. And in Roman numerals, it's just sort of going through all the numbers and then squishing them down into their addictive form, which does take a long time. But hopefully that's taught you how to do it, and now you can try it yourself and won't have to go through the pain of first of all adding all the numbers together without crossing these out, and then going through the pain of not including these two numbers, and then going through the pain of just learning how to do all of this, but you will, so. But it gets easier as time goes on. And this is always really good to know. If you want, you can because it took about 2 or 3 days to just memorize all of them. But it's no different to just going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you make a new digit. It's just every time you get to, like, instead of like going 1 to 2, you go from 4 to 5, and then you go from 40 to 50. That's the kind of thing that makes Roman numerals more difficult. And reading them, if it's an addictive form, it's relatively simple of just sort of, it's almost like sounding out a word. So you have, like, if I just write down like MMMCDCVI, that's a number, I don't know what it is. It's, so 3M's 3,500, 600, so we can see DC is 600, no tens, so then it's 6. And let's see if my skills are on point. This should equal 3606 in the 3000s column. And it does. So it's always good to have a website and a converter. And the hard part about doing math is, since everything's in subtractive form here, it all gets a bit messed up. But if you can convert your number from, so let's take 934, and there's 2 different ways you can write that, which is where it gets complicated with addictive and subtractive form. So 900, so it's 900, so DCCC, or MCM, 1000 minus 100, 30, and 4, IV, 2, 3, 4. I didn't even mix up the notation. But what gets really confusing is when you see on clocks, you have IV, or you have this on a clock, and then there's 9, you have IX, and then everything sort of gets thrown out the window with logic. But that's sort of how maths in the Middle Ages and the Roman Empire worked. And Roman numerals were really just invented to count under 1,000. They weren't meant for maths. They were meant for counting money and writing down pretty quickly. And you can do that, but once you try to do maths, everything gets a bit complicated. So I hope that's taught you a thing or two about numerals. Hopefully go try it yourself. It's pretty fun once you get the hang of it. But yeah, that's sort of it.